not, and, or, exclusive or, NAND, NOR, and exclusive NOR. These are the 7 types of logic gates used in computers. In this video, we'll take a look at each one individually to see how it works and how it behaves. And we're going to start at the top with the NOT gate. Here on the left, we have the symbol for the NOT gate, and here on the right, we have the truth table that represents the NOT gate's behavior. So the NOT gate is just an inverter. So its output will be the opposite of what you supply to the input. So if you inputted A, you would have an output of A bar, or not A. And here is the circuit that makes it actually work. If we make input A low, our transistor will be off. And this is because we have no base current. And if there is no base current, there is no collector current either. This means you have no voltage drop across the collector resistor, and so your output would have to equal your supply voltage. However, if you connected your input to the supply voltage, the transistor would be on. This is because we can now have a base current. This will pull the collector to ground and cause a current through our collector resistor. And because the collector resistor has a much higher resistance than the transistor does at this point, it will drop the full supply voltage, so our output will now be low. Now we can move on to the AND gate. On the left, we have the symbol for the AND gate, and on the right, we have the truth table that represents the AND gate's behavior. And if you notice, the only time the output is high is when both inputs A and B are also high. And here is what the physical AND gate circuit looks like. We have 2 transistors in series with each other, each controlled by a separate input. If we apply a low signal to the base of these transistors, we will have no base current, and both transistors will be off. And the resistance of the transistor when it is off is very high, so it is essentially an open circuit, and our positive VCC signal will not be able to make it to the output. This will cause our output to be low because there is no current flowing through our output resistor, and therefore there can be no voltage differential across it. Even if we give a high signal to just one of the base terminals, we'll find that our output will still be off. This is because our transistor with a low signal is still off, and this high resistance makes it impossible for our high signal at A to make it through. If we turn on only the second transistor instead, by giving its base a high signal, we will get a current to flow from the base through the emitter to ground, and our second transistor will become on, making it a very low resistance between its collector and emitter. But because of our low signal at our first transistor, that one will be off because there is no base current. And because the value of our base resistor will be much higher than the value of our output resistor, the voltage dropped across the base resistor will be much higher than the voltage dropped across the output resistor, and we can say the output is equal to 0 volts. The only way to get a high output would be to supply power to both of your base terminals, turning on the second transistor because of the base emitter current loop, therefore providing a low resistance path for our high signal at the A terminal, and turning on our first transistor. And because these transistors will have a very low resistance when they're on, our VCC signal will make it to the output, but only when our AND condition is met. If we add an inverting circuit to the output of our AND circuit, we now have a NAND gate. Its symbol is the same as the symbol for the AND gate, with the addition of a little dot on the end to indicate that the output has been flipped. And you can see in the truth table that it's the opposite of an AND gate, because when both the inputs are equal to 1, the output is off, and in all other situations, the output is 1. If A and B are both equal to 1, we get a current flow through our inverter base, and the transistor turns on. This pulls the output directly to ground through the low resistance. If the AND condition is not met, and AB is equal to 0, the transistor in the NOT gate turns off, and our output is pulled up to VCC through the pull-up resistor. Because there is no current flowing through the pull-up resistor, so there's no voltage dropped. So all an AND gate is an AND gate in series with a NOT gate. And the NAND gate is very special and very common because it's known as a universal gate. This means using only NAND gates, you can create every other type of logic gate. So I will make a separate video on how to make every single type of logic gate using only NAND gates. But for now, we'll move on to the next one. The next logic gate we'll take a look at is the OR gate. You can see the symbol for the OR gate in the top left and the circuit diagram for the OR gate on the bottom. On the right hand side, we have the truth table, and you can see that the OR gate outputs a 1 if either one of its inputs is a 1. Otherwise, it will output a 0. If we make both of our outputs 0, then both of our transistors will be off because we have no base current. This means our transistors have a very high resistance, and the VCC signal will not be able to make it through them. And because we have no current flowing down our output resistor, the voltage across the resistor will be 0 volts, and our output will be tied to ground, giving us a binary output of 0. However, if we change our B input into a 1 by providing it with a high voltage signal, we create a current through the base out of the emitter and down to ground. This will turn on our transistor, making it a very low resistance and allowing a current to flow from VCC through the output resistor through to ground. And because we can consider the transistor as a short circuit at this point, we can say that the output resistor will drop the entire supply voltage, and so our output will be high. So you can see if you switch the B output low and the A output high, you have the exact same result. And we can see there is no effect when we turn on both transistors compared to when we just turn on one. In either case, the supply voltage will be shorted to the output. So the OR gate is just a parallel set of transistors where if either one of them turns on, then the output turns on as well. Now we're going to talk about the NOR gate. And just like we could put an inverter at the end of an AND gate to make a NAND gate, we can do the same to an OR gate to make a NOR gate. So you'll see that the truth table for this logic gate is opposite of the truth table for the OR gate. The output of the NOR gate will only be 1 if all of its inputs are 0. If one input or the other input equals 1, then the output will be 0. And something to note, just like the NAND gate, the NOR gate is also a universal gate and can be used to make every single type of logic gate. So we can also cover that in a separate video. For now, let's just examine its behavior through this circuit. Let's say the output of our OR gate is high. This means either A or B is on. This will allow a current to flow through our base out of the emitter to ground and turn the transistor on. This will cause a current to flow from our supply voltage through our collector resistor, through the transistor into ground. And because our transistor is a short circuit, the entire supply voltage will drop across our output resistor, and our output will be at 0 volts. Let's say, on the other hand, both of our inputs are equal to 0. That will turn off the transistor in the NOT gate because there's no current flow through the base. And because our output can have no current flow due to the high resistance in the transistor, the voltage drop across the output resistor will be 0 volts, so our output will have a high voltage. So this is the exclusive OR gate, also known as the XOR gate, indicated by the symbol on the top left, and this positive sign inside of this circle also indicates the XOR function. So this is saying the output is A exclusive OR with B. If we look at the truth table, we'll see it's similar to the one we had with the OR gate, but with the exclusive OR gate, the output actually turns off when you have both 1s on your inputs. So the XOR gate needs exactly one of its inputs to be on in order to output a signal. And that's why it's known as a difference detector. So you can see this circuit is pretty complicated looking, but it's actually quite simple. And the Boolean expression that represents this circuit is shown above. The output is equal to A and not B, or not A and B. Now this section at the bottom is just an inverter, so we're calling the input to that transistor B bar, and the same is going to apply up here. So this A and not B is the equivalent of this A being in series with this inverted B signal, and this not A and B is this inverted A input here in series with our B input. And both results are in parallel, so they're being ORed, and that will make our output. So if we make both of our inputs 0, then we can say all of these transistors would be off because there's no base current. This means this transistor will be off too because there's no path for VCC to come through the base and out of the emitter to ground because this transistor is open circuit. So even though we have a path for current flow from VCC to ground through the base of this transistor, because this resistor has so much more resistance than this resistor down here does, this resistor will drop almost all of the VCC across it, leaving very little voltage for this one to drop, and we can say that our output is low. Now if we make A equal to 1 and B equal to 0, we'll cross off these two transistors because they will be off, but because we're providing a base current in this transistor, we're pulling it directly to ground, so we'll say that this would be a low signal here, and this transistor would be off as well. So now we have a path from our supply voltage down through this transistor to ground, which will turn that transistor on, which will provide a current path for our high A signal to ground, which will turn our final transistor on, providing a direct connection between VCC and our output, making our output high. If we instead make A0 and B1, we can say that these two transistors will be off, and because this transistor will be on, it will pull this point here directly to ground. Therefore, this transistor will also be off. And you can see we have a path for current flow from our B signal to turn on this transistor, which provides us a low resistance path to turn on the upper transistor and have our output be connected to VCC again. And if we make all of our inputs equal to 1, we can say that these two transistors will be off, and this is because of the two NOT gates that we made, which pull the bases of these two transistors to ground. So we know this transistor will be off as well because there is no path out of the emitter to ground because this transistor is open circuit. And again, we have this scenario where even though we have a current path from point B to ground, because this resistor at the base here has such a high resistance compared to this resistor at our output, we can say that the entire high signal from B here drops across this one resistor, and so our output signal will still be low. And that's how the exclusive OR gate works. So the final logic gate is the exclusive NOR gate. You can see in the truth table that it will output a 1 if its inputs are the same, unlike the exclusive OR gate, which would output a 1 if its inputs were different. That's because the exclusive NOR gate is the same as an exclusive OR gate, but at the output, we've added one more inverter. So if we perform the exclusive OR operation with A and B and get a 1, this transistor will turn on due to the base current, and our output will be pulled directly to ground and give us a low signal. However, if A exclusive ORed with B gave us a 0, then this transistor would be off, and because there's no current flowing through this resistor, there is no voltage across it, so our output is equal to VCC, and we get a high signal. And that summarizes the behavior of all of the logic gates. I think in the next video, I'll do a deeper dive into the NAND gate, and see if we can make every single logic gate using only NAND gates. So like and subscribe if you want to see that happen. And thank you for watching.